We would like to welcome our final oral presenter for today, which is Ms. Salma Izati Sinar Mashuri from UiTM Shah Alam. Let me introduce. Okay, Ms. Salma Izati Sinar Mashuri is a student at UiTM Shah Alam, currently pursuing a Master of Science in Applied Chemistry. Her education background is Diploma in Science at UiTM Tapa and Bachelor of Science in Applied Chemistry at UiTM Shah Alam. She is a member of Institute of Materials Malaysia, IMM, the Graduate Technologies and in Malaysia Board of Technologies, and Vice Secretary in UiTM Postgraduate Chemistry Club. Her research interests focus on photocatalysis, renewable energy, and environmental chemistry. So for today, her title is Zinc Oxide / Cadmium Sulfate Aluminum Oxide Support Photocatalyst in Organic Pollutant Degradation under LED Light. Please welcome.
Bismillahirrahmanirrahim. Thank you to the chairperson, Ms. Aisha. So I am Salma Izati Sinar Mashuri from UiTM. Would like to present about zinc oxide cadmium sulfide photocatalyst in organic pollutant degradation under LED light. So annually, about 300 to 400 million tons of organic pollutant has been produced by industries such as pharmaceutical, agriculture, food, and textile. So this industry produce abundance of organic wastewater. With the unwell treatment, it will cause the water pollution. So this industry is searching the best technology that has lower production cost, lower handling cost, and effective technique. So photocatalysis has been proposed as the technique to overcome the problem. So conventionally, zinc oxide was used as the photocatalyst because it has good thermal chemical stabilities and also stable optical features. However, there are some problems with zinc oxide such as fast electron hole recombination, large band gap because it only active in UV light. So to overcome the problem, cadmium sulfide was proposed in this research because cadmium sulfide is the photoabsorbance in the visible light and it shows high potential based on previous study in degradation of organic pharmaceutical waste. So the objective of this research, first, synthesis and characterize the photocatalyst, zinc oxide cadmium sulfide. Second, to study the performance and photocatalytic activity under LED visible light source. So compared to the other study right now, the light source used is halogens, which we know that halogen need high energy compared to LED. Alright. And the third one is to investigate the active species that are responsible for MB degradation. Okay, for scope today, we start with synthesis of photocatalyst, second characterization, next photocatalysis reaction. We want to know the optimization of parameter, and lastly, scavenger test and recyclability test. So this is the synthesis method of zinc oxide cadmium sulfide by way impregnation method. Okay, so the composition between zinc oxide and cadmium sulfide during this research was varied. Different molar ratio. So we have Z3C1. So Z means for zinc oxide, C for cadmium sulfide. So this one is rich in zinc oxide in the composite. Next is the same molar ratio between zinc oxide and cadmium sulfide. And lastly, rich in cadmium sulfide, which is Z1C3. This is the photocatalysis reactor that equipped with 21 watt LED visible lamp. Alright, we entered to the characterization. This one is optical characterization. So from UV vis and IR, we can get the reflectance edge. So to study the band gap, we calculate through the top plot. So we can get that band gap of pure zinc oxide originally is 3.30 electron volt. So when we added more cadmium sulfide, the band gap become decreased from 3.30 become 2.46 electron volt. So we already know the band gap. How about the position of the valence band and conductive band? So From the molten electronegativity, we can calculate here that from the valence band here that not significant difference between the photocatalyst. However, in conductive band shows the significant difference from pure zinc oxide with the loading cadmium sulfide. So the lowest conductive band we get is 2.34. So we move to the morphology analysis. This is the pure zinc oxide. Meanwhile, this one is the pure cadmium sulfide. So when we introduce a small amount of cadmium sulfide, the morphology almost similar, which is variety of tiny 3D geometric and formation of coral-like structure. With the similar amount, if appear as nanosheet layer with small agglomeration at the edge, and higher in cadmium sulfide shows agglomeration with small hexagon flakes. Okay, next is the Xrd analysis. The triangle one is the zinc oxide peak, meanwhile for the circle one for the cadmium sulfide. So it can confirm in the composite that we can see both characteristic inside the photocatalyst. So the photocatalyst shows as crystalline. Okay, what happened to the surface analysis? So compared to the pure zinc oxide, for surface area, when we loaded more cadmium sulfide, so the surface area become lower, the total pore volume become decreased and mean pore diameter become increased. However, the type of pore still in mesopore. So what is the advantage of mesopore? Because it has hysteresis from isotope plot here. So what is hysteresis? Hysteresis is where the material can able to do adsorption and desorption. All right,
Sorry,
next
Miss
we
Salma.
move.
You have another 5 minutes to complete.
All right, okay. So we move to photocatalytic studies. In molar ratio between zinc oxide and cadmium sulfide, we can see here that Z3C1 achieved 100% degradation within 130 minutes. This is due to rapid electron transfer at the interface between zinc oxide and cadmium sulfide. So it decreased the recombination inside the zinc oxide of electron and hole pair. And then the presence of cadmium sulfide, it reinforces the visible light absorption. So more incident photon will be harvested and increase the photoactivity. Next is the initial concentration of MB solution. So we can see here in 3 milligram per liter shows higher degradation because hydroxy radical effectively collide with the MB molecule. However, in lower initial concentration, so lower methylene blue pollutant available inside the solution and then less adsorption. So it makes the degradation lower. Meanwhile, at the higher concentration, because too much MB pollutant inside the solution, so MB molecule hindered the path length for the photons to penetrate the solution. Next is the catalyst loading. Okay, we can see here that increase the catalyst loading can increase the adsorption. However, when less amount of photocatalyst is loaded, so less amount of methylene blue in contact with photocatalyst, so lower degradation. Meanwhile, too much photocatalyst can cause Rayleigh scattering phenomenon. This is caused by the photocatalyst particle size and abundance. So less amount of light can travel through the wastewater sample. Okay, next is pH of MB solution. The best one is pH 9 because more free hydroxyl radical produced by hydroxyl ion and hole. For pH 3 and 7 shows less degradation because of the solution. So we want to determine either this photocatalysis activity is confirmed photoactivity. So we do the adsorption test. So the highest adsorption can achieve only 44.97. So area under the graph more than blue line is confirmed is photocatalytic reaction by degradation by the active species. So we want to know what is the active species available inside the solution. We do the scavenger test. So the reagent can is determine the specific active species. So we can see here that electron and hole is generated from the photocatalyst. However, the major active species that degrade the methylene blue we can see here is hydroxyl hydroxyl radical and also superoxide. And the recyclability test can be up to 4 cycles. And then the proposed mechanism is, okay, firstly, we see at the valence band where originally here is the electron. So when photon from the light source attack the electron will obtain the energy and then it will excite and jump towards the conductive band, leaving behind a hole. Okay, so these both simultaneously, electron and hole, will travel to the surface. Okay, we see at the valence band what happened. When water molecule react with the hole, it will become hydroxyl ion and hydrogen. And then further the reaction of hydroxyl ion react with hole, it will become hydroxyl radical. So this radical responsible to degrade the methylene blue. So at the electron, when react with diffuse oxygen, it will produce superoxide. So superoxide has two role here. First, directly degrade the methylene blue. Another one, when react with hydrogen ion, it will become OH2 radical. So react with another OH2 radical will become oxygen and hydrogen peroxide. So hydrogen peroxide react with superoxide will become hydroxyl radical and hydroxyl ion. So the radical will react with methylene blue and degrade it. Okay, another role for electron is when it react with hydrogen peroxide, it will produce hydroxyl ion and hydroxyl radical. So this radical will degrade the methylene blue. So as a conclusion, we can use zinc oxide cadmium sulfide because it has high crystallinity, high surface area, has 3D morphology and lower band gap. Okay, for the best photocatalytic performance can achieve is 100% within 90 minutes. So the scavenger test proved that the presence of electron and hole generated from photocatalyst, meanwhile hydroxyl radical and superoxide were active species that responsible to degrade methylene blue. So zinc oxide cadmium sulfide is the promising photocatalyst in degrade methylene blue solution and can be further analyzed for the other type of organic pollutants. So thank you.
Okay, thank you, Miss Salma, for the fruitful sharing. Okay, now we move on to the Q&A session. Okay, there is one question in the chat room. Let me read for you. Okay. The question is, please justify how did you determine the energy emitted from the LED? So it's UV active or vis active?
Okay, to determine the energy emitted from LED is by the bulb that we use. So we know from the bulb we use the visible active. So to know the material is active in UV or visible, we see from the reflectance age first from UV vis and IR result. So when it fall at the lower than 450 nanometers, so that one fall in the UV region, while for higher than 450 nanometer, that one fall in the visible region. So that is the first step that we want to know that our photocatalyst can be used what type of light energy to activate it.
Okay, thank you. Another question. Okay. You used cadmium to mask the disadvantage of zinc. However, did this composite compromise each other?
Okay. For cadmium and zinc, it has synergy between each other. However, if too much cadmium sulfide, it will become the self-attack based on the previous study also. So the optimum amount of cadmium to work with zinc oxide must be obtained. So that's why Z3C1 is the best photocatalyst.
Okay, Miss Salma, is there another question? Okay, we have another question. Okay, have you tested the recyclability and reusability of your compound? How many times can we use it for dye degradation?
Okay, based on my slide, so 4 cycle can be met. So the lowest one is 46%.
Okay, 46%. Okay. Thank you, Miss Salma, for
Okay, you're
the wonderful
welcome.
sharing.